Alright, in this video we're going to cover light emitting diodes, or LEDs. So as the name implies, these are diodes that emit light. So the math is going to be exactly the same as what we saw. It really doesn't like it when I write at the top there. It won't let me close my parentheses. Oh well. The math is going to be exactly the same as what we saw in the previous video. The circuit symbol is almost identical, except we have two little arrows coming off like this, indicating that it is emitting light. And the very common task you're going to need to do when using LEDs is if you have some voltage source, whether it is a battery or a pin on a microcontroller like an Arduino, and a resistor in series with the LED, you know your voltage source. That's usually a given, something like 3 volts from a battery pack or 5 volts from your Arduino. You know the forward voltage drop of the LED, which has a range from roughly 2 volts for red up to around 4 volts for blue. It's going to depend on the specific LED. You're going to need to look at the data sheet, but remember that's higher than the roughly 0.7 volts we saw for common diodes in the previous video. So you know your source. You know the forward voltage drop across the LED. You also know the current rating through the LED, which for typical LEDs, the little indicator lights we see on everything, is usually going to be in the milliamp or very low tens of milliamps range. So 20 milliamps, for example, is a common value. That's how much current the LED can handle before it burns out. So the question you then have when designing a circuit with an LED is, okay, what should this resistor value be? That is called your current limiting resistor, because, as the name implies, it limits the amount of current flowing through the LED. And a common question students usually ask when they initially get this explanation is, well, why do you need the resistor at all? Why don't you just hook the LED up directly to a power supply that has the exact voltage you need? And there are sort of two different explanations for that. So again, the question is, why don't you just do this? For example, if I have a red LED that I know has a forward voltage drop of 2 volts, why don't I just hook it up to a 2 volt power supply? And on one hand, power supplies typically only come in certain values or common voltages. So for example, USB power provides 5 volts, and something like an Arduino that's running on USB power is going to use 5 volt or maybe 3.3 volt logic. Or if you are using batteries, individual AA batteries, alkaline batteries provide roughly 1.5 volts, but in reality that can be a little over even 1.6 volts when they're new and getting down closer to 1 volt as they drain, so that is not constant. So it's hard to find either, unless you have a laboratory grade benchtop power supply where you can turn a knob and select the exact voltage. For common circuits, either wall powered or battery powered, you might not have something that is the exact voltage that you need for your LED, or that voltage might change as the battery drains, so you're not going to have exactly what you need for your LED. And then second, remember that the idealized diode model, we treated it like this, okay, we just have this perfectly constant forward voltage drop on an IV curve. So we say, oh, that's exactly the voltage drop I need across my LED. But in reality, this is a really, really steep curve. So if your power supply, if the voltage is even just a little bit too high, say you have 2.1 volts instead of 2 volts, and that current is going to shoot off really, really high, way more than your 20 milliamps, and burn out your LED. So the safe thing to do is put a current limiting resistor in series with your LED and do the calculation to figure out what this resistor value should be to limit yourself to that safe current. So we'll work through an example here. Say, again, I'm using USB power, so I have 5 volts. I have an unknown resistor R. I have a single LED. And I'm going to say I have a forward voltage drop of 2 volts across that, and I want a current of 20 milliamps through the LED. What should this resistor be? Okay, so I know I have my source voltage here, 5 volts. I know I have a 2 volt drop across the diode because the diode is forward biased because my source is greater than 2 volts. Even if I keep increasing this source voltage, I'm still only going to have a 2 volt drop across the diode. We covered that in the previous video. So I can apply Ohm's law to my resistor, where I know that V is the drop across the resistor, so that's going to be 5 volts minus 2 volts. And I know I have my desired target current is 20 milliamps or 0.02 amps. I don't know R, so I can rearrange that to solve for R. That's going to be 5 minus 2 over 0.02. And in this case, that gives me 150 ohms, which happens to be a common resistor size. But if I got some funny value there, then remember that I could either combine multiple resistors in series and or parallel. This is covered much earlier in this playlist to fine tune and get the exact value that I need. Or I can just choose a slightly larger resistor value. Say if I only had 220 ohm resistors, I could go up to the next biggest size I have to stay on the safe side. That is going to lower this current. But in practice, in terms of visibility to the human eye, you're probably not going to see a huge change in brightness of the LED with that slightly lower current. So if you look up an LED datasheet, sometimes there will be a separate graph, not just the IV curve, but showing luminosity against current, so you can see how much the brightness will actually change with the current. In practice, it's going to be visible to the human eye, again, even down in single-digit milliamps many times. So better to play it safe and go up with a bigger resistor as opposed to going down to, say, a smaller 100 ohm resistor, increasing that current and risking burning out your LED immediately or decreasing its lifespan. We are not going to spend a ton of time on it in this video because if you were on YouTube, I have other videos covering more examples for this on my channel, but that are not part of this playlist, just kind of a more practical dealing with LEDs video. If you have multiple LEDs, you can put them in parallel, each with their own current limiting resistor, and in each case here, I didn't draw the little arrows on all of the LEDs. If that's your source voltage ES, each LED resistor pair here just has the source voltage across it, so you can just do this calculation individually, again, where your resistor value for each one is going to be the battery voltage minus the forward voltage of that particular LED divided by the target current of that particular LED, which might be different. Again, if you're mixing different colors, for example, the forward voltage drops are going to be different. Depending on the voltage of your battery, you could be dropping more voltage over the resistor here than you need to. So for example, say I had two LEDs with a 2 volt forward voltage drop, but I have a 5 volt supply. I could combine those two LEDs in series like this. So now I'm going to have my current limiting resistor there. And for a 5 volt supply, now I'm going to have a 2 volt drop over each LED. That is going to add up to 4 volts over the two LEDs since they're in series, and now I'm only dropping 1 volt over the resistor as opposed to this configuration where I would be dropping 3 volts over the resistor. So if you then look at the power dissipated by the resistor, P equals IV equals I squared R or V squared over R, however you choose to calculate it. Technically, in that situation, this configuration is a little more efficient because you're not dissipating as much power in the resistor. You also always need to be careful that you are not exceeding the power rating of your resistor. So regardless of how you design the circuit, you might be getting the target current through your LED, but you don't just have to think about the LEDs, you have to think about burning out the resistors too. So whenever selecting current limiting resistors, if you try to do something, for example, like getting away with doing this, just using one resistor in series with a whole bunch of LEDs instead of giving them each their own individual resistor, you need to do that power calculation to make sure you're not burning out this resistor. So again, not going to work through mathematical examples for all of that here. I have other videos covering that, but this was an overview of the basic idea of how do you do the math to select the current limiting resistor value as opposed to being given a circuit and asked to solve for the current. This is when you know the current, you know the voltage drop, you know the voltage supply, and you have to pick this resistor to avoid burning out your LED.